In this video, we continue with the topic family of spheres. Before that, let us quickly recall what was done. S stands for the expression x square plus y square plus z square plus 2ux plus 2vy plus 2wz plus d. And if you put s equal to 0, you have a sphere with center minus u minus v minus w and radius u square plus v square plus w square minus d, radius squared. We have taken u to stand for the expression alpha x plus beta y plus gamma z plus delta, and if you put u as 0, you get a plane. If gamma are the points which are common to s equal to 0 and u equal to 0, you get a circle. And if you look at the equation s plus lambda u equal to 0, you get a family of spheres, each passing through the circle gamma. This is what we had done earlier. Okay, so if you want to represent a circle in the three-dimensional space, this is one way of doing it. Take the sphere and take a plane which intersects that sphere. You get a circle. So if you want to represent the circle, think of two suitable surfaces, out of which one should be a sphere and the other one should be a plane. Okay, now we are going to look at the circle as an intersection of two spheres. Look at this diagram. So S1 equal to 0 is a sphere, S2 equal to 0 is another sphere. The claim is that the points which are common to both is a circle. So the points which are common to both I am representing by this curve. I am calling it as gamma. Now we will prove that gamma should be a circle. So when I say S1 equal to 0, what do I mean? So S1 will stand for that is S1. If I want S2, I replace the 1 by 2 on both the sides. Alright, so I will use a short notation. Si is equal to all this, where I have ui, vi and wi and di, and I'm going to consider I to be equal to 1 and 2. So when I is equal to 1, I get S1, and when I is equal to 2, I get S2. Alright. Now let x, y, z satisfy S1 equal to 0 and S2 equal to 0. So in other words, I am choosing a point on gamma. Alright. Look at S1 minus S2. S1 minus S2. So if you have XYZ satisfying this and XYZ satisfying this, XYZ will also satisfy this. But let us look at what S1 minus S2 is. So if you do S1 minus S2, the term x square, y square and z square will cancel off. So you will actually have an equation in x, y and z. What does that mean? It means that S1 minus S2 is actually a plane. Alright. So a simultaneous solution of these two equations is also a solution of this equation. Namely, point which is common to the two spheres lies on a line. But then we know that the intersection of a sphere and a plane is a circle. Alright. So the points which are common to the two spheres is also on this plane. Alright. But S1 equal to 0 sphere, S1 minus S2 equal to 0 plane, points which are common to these two must be a circle. But then this circle cannot be different from the circle S2 equal to 0 and the plane S1 minus S2 equal to 0. Why? Because you're looking at a simultaneous solution of this and also this. So I hope it is clear to you that the curve gamma is actually a circle. A much more elaborate and detailed argument can be given as an if and only if statement, but I'll just leave it here, and maybe you can give a little deeper thought. So essentially that will be the argument. Okay, so we will now take this as a fact that if you're looking at S1 equal to 0 and S2 equal to 0, you're actually looking at a circle. Okay. S1 plus lambda S2 equal to 0 is a family of spheres. Is a family of spheres. Why is it a family of spheres? So, you know, this expression on the left hand side will be an equation of this kind. All right. Okay, so I'll just write it and show it to you. Is a family of spheres. Anything special about this family of spheres? Each member of the family containing the circle okay, let me write this equation. So this is this, or we are looking at x square lambda x square, that's here, y square plus lambda y square is here, and similarly z square plus lambda z square. Now let us look at these terms, this and the one corresponding to that over here. All right. Something has gone wrong here. So lambda is multiplied to this whole thing. Okay, please correct that. Okay, yeah, I'm looking at S1 plus lambda S2. Okay, all right. So this and the term over here. So what I have is twice u1 plus lambda u2 x, twice u1 plus lambda u2 x, 2x common. Similarly, twice v1 plus lambda v2 y plus twice w1 plus lambda w2 z plus d1 plus lambda d2 is equal to 0. Now obviously you can okay, so if you want it to look like an expression of this kind, you can divide both sides by 1 plus lambda. Let's do that. Okay, or x square plus y square plus z square plus twice u1 plus lambda u2 x divided by 1 plus lambda plus twice v1 plus lambda v2 divided by 1 plus lambda y plus twice w1 plus lambda w2 divided by 1 plus lambda z plus d1 plus lambda d2 by 1 plus lambda equal to 0. Alright, so this is the equation of a sphere. So you have x square plus y square plus z square. You can call this as capital U. So 2ux plus, you can call this as capital V. So 2vy. You can call this as capital W plus 2wz. And you can call this as capital D. So you get a sphere. Now you have to be a little careful while dividing by the quantity 1 plus lambda. You have to make sure that lambda is not equal to minus 1. Because if lambda is equal to minus 1, you don't get these terms. Alright, you don't get the squared terms, and what you actually get will be a plane. Okay, so you won't get a sphere but a plane. So one has to be careful carrying out this division. Okay, so once you have the equation in this form, then it's not difficult to write down the center. The center will be, so this is 2 times u, so the center will be just minus of this thing. Okay, and so the coordinates of the center, so let me just write it. The center will be minus u1 plus lambda u2 upon 1 plus lambda minus v1 plus lambda v2 by 1 plus lambda minus w1 plus lambda w2 divided by 1 plus lambda. That would be the center, and you can write out the radius. So this is, let's say, u, v and w. All right, the radius will be u square plus v square plus w square minus d, where we can call this as d. Okay, so the radius squared is equal to this. Okay, now we have a certain problem over here. Okay, so we may not get, so out of this family, for those lambdas which don't give this to be a quantity greater than or equal to 0, we may not get a sphere, because if radius squared, radius is a real quantity and its square will always be greater than or equal to 0. It cannot be a negative number. So let me just pause this here for a minute. Okay, so I would like to write this expression and show you that the coefficient of lambda is an important object. Let's see that. Okay, so u square plus v square plus w square minus d. I wish to write an expression for this. So what I have is u1 plus lambda u2 upon 1 plus lambda square plus, now this minus sign has got placed at the wrong position. It should be somewhere here, and same with this, it should be somewhere here. So minus d all right. Now I can multiply the entire inequality by 1 plus lambda whole square and simplify it. That's what we get. Okay. Or u1 square plus let me write it like this. So lambda square times I have u2 square plus v2 square plus w2 square. So I'm looking at the terms coming from these terms, okay, and minus d2 plus lambda times something. So lambda times 2 u1, so 2, I'll take 2 as common, u1 u2 plus v1 v2 plus w1 w2 and minus d1 minus d2 and the constant term. The constant term is u1 squared plus v1 squared plus w1 squared minus d1, and this should be greater than or equal to 0. So I was telling you that there's something interesting about the coefficient over here. Let me make a correction. I noticed that this 2 is not there with d1 and d2. So one second. The 2 is with this term, with this term, and with this term. Okay. Let me write this clearly over here. So coefficient of lambda. So what is the coefficient of lambda? It is twice u1 u2 plus v1 v2 plus w1 w2 minus d1 minus d2. That is the coefficient of lambda. Okay. And in a later video we will see that the condition of orthogonality for two spheres S1 equal to 0 and S2 equal to 0 is precisely if S1 equal to 0 is orthogonal to S2 equal to 0, then u1 u2 plus v1 v2 plus w1 w2 will turn out to be d1 plus d2 upon 2. So we'll see this in a later video. So I will just stop at this particular point, and in the next video we will discuss orthogonality of spheres.